Okay, thanks, Max. Is the screen share okay?
Yep, looks good.
All right. Yeah, so like Max said, I'm Megan, and today I'm going to talk to you guys about a term project that I did last semester about ransomware in industrial control systems, and more specifically in energy systems like power grids. So I guess first, as a disclaimer, I picked this project with the intention of showing to the cybersecurity community why and how power systems are less vulnerable to some of the common types of cyber attacks than they like to believe. Power systems in particular are built to be resilient against a variety of natural and man-made threats. So from my research perspective, cyber attacks are just one new type of threat that they must adapt to. So for those of you familiar with power systems, the fact that they are in fact resilient to some level of cyber attacks may not be surprising, but I did find some things along the way that surprised me, so I hope you'll find this interesting too. But yeah, security researchers have a tendency to group all things industrial or IoT together, and I happen to believe that these are very different types of systems, not just from a process standpoint, but also from a security standpoint. So anyway, we know that ransomware can be a huge headache for companies. In addition to slowing down work, it's costly to recover from, whether by trying to restore files manually or by paying the ransom. And trends indicate growing concern over ransomware and evidence that industrial control systems may be targeted more and more. So an evolving area of research is what this really means for industrial control systems. Specifically, can ransomware infect the right resources in these systems to prevent them from operating safely, or does it just shut down the IT side of things? Well, the answer is yes, it can. In February of this year, ransomware infected some HMIs, polling servers, and data historians at an oil pipeline company and forced their company to shut down for 2 days, even though the PLCs themselves were not infected. Even more recently, just in September, a utility in Pakistan called K-Electric that supplies power to Karachi was infected with ransomware. This one didn't affect the actual power supply, but it did take down many online services, including call centers. And so while this may not seem as significant, targeting call centers was one of the key parts of the Russian attack on the Ukrainian power grid a few years ago, as part of an effort to mask the attack and prevent customers from being able to report outages. So even things like this that don't directly affect the process control may have an operational impact on the way that the system works. So let's take a step back and talk about ransomware. Ransomware is a financially motivated malware that encrypts or blocks access to data and demands payment in order to unlock the files. Some companies pay, some companies don't, but even if you don't pay, it can be expensive to recover from. For industrial control systems like energy, oil and gas, transportation, manufacturing, losing access to computing resources could actually shut down your physical processes, or in the worst case, cause safety incidents. However, it's generally considered harder to create a successful campaign that will penetrate the operational technology or OT network. And if it requires a higher investment from attackers, my hypothesis was that financially motivated attackers would be less likely to focus on these types of targets. So the goal of my research was to figure out if there was evidence of this trade-off between the cost for an attacker and how easy it was, and also to analyze what types of OT devices would actually need to be infected to cause operational impacts on a power grid. So let's talk about what separates an ICS target from an IT target in a ransomware perspective. ICS systems tend to have legacy systems, which means that they have old and known vulnerabilities, which is very attractive for ransomware. In addition, companies lose money immediately if they cannot deliver product, which means availability of systems is a high priority. And when we compare that to IT systems, usually they want to protect confidentiality and integrity of their data, and it's okay if servers go down for a short period of time. So next, what makes energy systems unique among ICS systems? Well, a successful attack will impact everyone in range immediately, and if power grids go down, it can have cascading public health and safety consequences. In general, patching is less common across all ICS devices, but compared to other industries, updating your devices with the new software may actually be impossible, because if it reduces backwards compatibility with other devices, you're just not going to do it. Even if updates are improved, you can't just restart the power grid or restart the systems governing the power grid every night. It has to come at scheduled maintenance intervals, and these are usually pretty far apart on the scale of years. Another constraint on power systems is the need to balance load and generation, which requires a higher level of visibility into the system at any given time. One other unique part about the power industry compared to others is that they have regulatory bodies setting standards for cybersecurity, and they issue fines for non-compliance. I couldn't find similar governing agencies that set cybersecurity standards in other industries. There's some in healthcare, and even some in oil and gas, but mostly they make recommendations rather than requirements. So with this knowledge in mind, I wanted to start with a survey of ICS security events in order to find out how prevalent these kinds of attacks really are. It's difficult to find publicly available information about security events, but the best publicly available data set I found was from the US Cybersecurity and Infrastructure Security Agency, or CISA, and their NCAPS database. I also found a useful set from Kaspersky, which is a cybersecurity company. I studied the years 2016 to early 2020, and I started in 2016 because that kind of seemed to be when trends of ICS ransomware started to rise. So I broke down all of the ICS security events by which ones were ransomware, which ones affected the energy industry, and which ones were actually ransomware that also affected the energy industry. The data sets I have are admittedly pretty small, but you can see that ICS ransomware events seem to be about half of all cybersecurity events, and half or fewer of the events impacted the energy sector. Only 1 or 2 events of energy ransomware occurred every year, and according to this data, none of them occurred in the US. This data kind of seemed to support my hypothesis that ransomware attacks on energy systems were rare, and the cases where they did exist were almost exclusively collateral damage of larger campaigns rather than targeted attacks against those specific companies. So it's one thing to know that these attacks occurred, but to really understand what was happening, I wanted to know what kind of impact the attacks had. I found that a large majority of attacks had their main impact only at the business or enterprise level. Still, almost 30% of campaigns did impact process control. This was not always through a targeted attack, but also covered cases where there was enough collateral damage to cause an impact on process control systems, like it just spread through the network far enough. Or because of the impact on the enterprise system, the company chose to shut down the operational components until they were able to restore everything. Additionally, some processes were able to continue to run at a limited capacity or with delays, but if the ransomware impacted the operational status of the system at all, it got grouped in this category. Only 3.7% of events were reported to impact only the public interface. So that's kind of like the website, the ability to pay your bills online, to get updates, things like that. Some of the enterprise systems may have also had their public interfaces go down, but because the damage to internal systems was more significant, it was grouped in that category. And there were no reported incidents with no impact, which may seem counterintuitive, but it actually makes sense, because if they had no impact, these events may not have been reported, or they may have even gone undetected. So to compare the trends with cybersecurity across many industries, I also wanted to narrow in on specifically the perceived risk of cybersecurity events from an energy perspective. In the US, federal law requires utilities to report all electric disturbance events. And I compared the events that were related to cyber attacks or cyber faults with suspected vandalism or physical attacks, because both of these represent potentially malicious external threats rather than operational errors or weather-related events. So cyber events were reported either as suspected cyber events or cyber events that could potentially impact system. And I found 17 of these in just over 4 years. Only one of these had a known impact, 3 had an unknown impact, and the rest had no impact on operations. And I compared that to physical attacks and vandalism, which had a reported 264 events, where 33 of them caused a known impact. The impact of these physical attacks and vandalism affected and caused thousands of additional megawatts of load to be dropped. Weather and operations, which are not shown in this table, had a much higher impact on customers and caused even more load to be dropped. So from this perspective, it's understandable why utilities may not be as concerned about cyber attacks, but it's also evident from the single event that affected over 23,000 customers why they can't totally ignore it. So I actually did some digging into this specific event, and I found that it was a cyber attack on a solar provider in the covered area in California, Utah, and Wyoming. They lost visibility into their SCADA system as a result of the attack, which was a denial of service attack on the Cisco firewalls that they had on their industrial control network. And the attack forced the routers to reboot. So the outages themselves lasted less than 5 minutes, and the devices were rebooted over a 10-hour period. It's not believed that this was a targeted attack that was trying to do anything specific to this solar company. They just happened to be hit by it. And it's not exactly ransomware, but it's kind of an example of the same type of category of cyber attack that ransomware would fall in, just that it's low-hanging fruit that can kind of be broadly deployed on the internet to just see how many people you can affect. It's also similar to ransomware in that it blocked the availability of a resource. So it's a good example of how the effects of ransomware can have an operational effect on the larger grid. So the second part of my study was to simulate what would happen if a power grid did experience a ransomware attack on OT equipment. I modeled a system in PowerWorld, just a standard 37 bus case, and I assumed that ransomware would make a resource totally unavailable. I chose 4 components to simulate a ransomware attack on, and chose these specifically based off of successful ransomware attacks on other ICS systems. I modeled the loss of the historian as an inability to respond proactively to expected peak loads. So instead, the system only adjusted reactively, which is kind of what it does anyway, so that wasn't really a huge deal. The loss of the engineering workstation I modeled as a loss of visibility into relay and breaker statuses. And so instead of making decisions, instead it only made decisions based off of voltage and frequency measurements. This one was probably a little bit of a stretch, but seeing as workstations can be used to reprogram relays, breakers, and PLCs, it seemed like this would be the worst case scenario. So if the engineering workstation was attacked and the ransomware affected it and was somehow kind of able to spread to your ability to see what the breakers were doing, again, probably a little bit of a stretch because you would have other measurements that would let you see that sort of thing. But this seemed like the worst case to consider. Infecting the application server meant that data could still be measured, and so you could still achieve stability, but the servers that calculated your optimal dispatch couldn't be used. And finally, infecting the database server represented a total loss of visibility into the measurements, which is kind of like, yeah, loss into a centralized SCADA. So if there was distributed SCADA components, those were still operational. But in terms of like centrally operating anything from a control center, that may have been unavailable. So for this presentation, I'm just going to focus on the application server because the first 2 situations are pretty uninteresting. The system is still able to function. I guess it's possible that if you had an unusually high load or unexpected peak. The lack of historical data could impact your load forecasting enough to cause an impact, but that seems unlikely. And again, with the engineering workstations, even if you couldn't see the relay statuses, that would really only matter if there were faults that occurred, which I didn't simulate in the study. And of course, compounded events are always going to have a bigger impact, whether they're natural or through a cyber attack. So, you know, we could start modeling losses of different lines combined with different cyber attacks. But that's really just going into different, you know, kind of N-1 and N-2 reliability analyses. So I programmed a dynamic load throughout the day to mimic a normal day. It simulates low, medium, and high loads and reaches a peak of 90% of generation capacity. When the optimal dispatch is turned off, the marginal costs increase, but we can still see that it's proportional to the total amount of load. The losses in the system added up to over $100,000 in a single day, which is pretty significant for as small of a system it is. So you can imagine that if it was a much larger system, these costs could add up pretty rapidly, and the inability to effectively or optimally dispatch your power in terms of cost could have a real impact on the system. So the main takeaways from the first part of the study were that ICS malware is definitely on the rise, and that ransomware that targets or accidentally hits ICS systems is keeping pace with it. However, there's not much evidence of targeted ransomware attacks against the energy sector, although they're still being hit with the same sort of things about proportionally with the rest of ICS systems. And I guess that was one of the things that surprised me the most, was that I expected them to be targeted less, and I'm not sure that that was true, but it was true that the attacks they did experience were not necessarily getting deep into their systems. Yeah, so it seemed like the easiest attacks to compromise on the OT network had the least impact. So if you think about a historian, that might be something that you would want to access from a higher level in your network. If you were doing longer term studies or something from an engineer who's working on the business network, you know, they might have access to the historian. And so there might be an easier path for ransomware to that kind of device. But that had one of the lowest impacts on the actual operation of the system. Without infecting the actual PLCs, the situation that would cause the most impact is compromising a database server, which would reduce the system to manual operation, but that's still not a full total shutdown. At the least, ransomware may cause an impact to generation costs, which could be significant over a certain period of time. So even if the system is capable of operating, it would be interesting to study what decisions that utilities are likely to make if they did experience an attack on the OT network. The oil pipeline that I mentioned at the beginning made the decision to shut down their operations after the historian was infected, but I'm not sure if a utility would make the same decision because they need to keep power on for their customers. Another remaining question is what would be the best way to protect ICS devices from ransomware, given the limitations that we discussed at the beginning, specifically the lack of the ability to patch or update systems and the necessity to keep systems online as much as possible. So I think that's all I had for today. I know it's pretty quick, but happy to answer any questions either about the study or about ransomware and power systems in general.
Hey, Megan.
Yes.
Kind of a question. So according to your understanding on this topic, how good are the attackers these days? Are they already very good, and that is how much damage they can do, or they are still in a very early stage of training themselves, and they could potentially cause a much more significant damage to the system if they get trained much better?
So I guess I didn't go so much into the other side of this, but what I studied in this was sort of your lower level of attackers, financially motivated. Usually they would buy the ransomware from some other online vendor and then choose their targets, or they may even buy, they may even have their own ransomware and then buy the access to their targets. So it's kind of a game of money to them. You know, I'm going to invest this much and then I'm going to demand a ransom to see how much I can get all back. So really they're targeting easy targets. That's why we see a lot of municipal, city, county governments being hit with ransomware. My opinion is that the bigger threat to the grid and to energy systems is going to be more advanced, more motivated, maybe not so much financially motivated, but politically motivated attackers. So either nation states themselves or groups that are funded by nation states, and that's not going to be ransomware. You know, they're not going to demand money. They're just going to take it out. So I think there's kind of two classes of attackers, and the goal of what I was pointing out with this study was that not that we don't have to be worried about attackers or that we don't have to worry about more advanced attackers, but that this lower class of attackers is not as much of a threat to systems that are already built to be very resilient.
Yeah. Okay, so that is good to know.
Any other questions? Nope, doesn't look like it. So thank you very much, Megan. Up next, we have a presentation by Phuc Huynh. Phuc Huynh is a PhD candidate at the University of Illinois at Urbana-Champaign. He received his bachelor's in science from the University of Minnesota Twin Cities in 2013 and his master's in science from the University of Illinois at Urbana-Champaign in 2016, both in electrical and computer engineering. Building a sustainable and energy-secured future is Phuc Huynh's major interest. The interest is being realized through the creation of a highly efficient, reliable, and compact electromechanical conversion systems for offshore wind energy harvesting.
Yeah, okay, thank you, Max. Can everyone see my screen and hear me?
Yep, looks good.
Yep, okay, perfect. So thank you everyone for joining my presentation today. Today I will present about the work for my PhD here, a portion of it. And the title is Integrated Generator-Rectifier Co-Design for Offshore Wind Turbines. With this work, we would like to acknowledge the Advanced Research Projects Agency, OPRE, and the Granger CNE for funding this project. So why am I caring about the offshore wind turbine? Because the offshore wind is a very huge, a massive potential resource of energy for the U.S. only. According to the estimation, if we fully take advantage of the offshore wind resource, each year this resource can produce 2 times the entire U.S. annual electricity consumption. However, there is a really big obstacle to prevent offshore wind to become a major resource of energy. That is because the levelized cost of electricity, or LCOE, is still relatively high for offshore wind. In particular, if you look at the number today, the offshore wind LCOE is standing well above $120 per megawatt hour compared to the onshore wind, which is standing at $40 US per megawatt hour. Compared to other energy resources, in order to make offshore wind a viable resource, the LCOE has to go lower than the current value, and it must reach the level about similar to coal or nuclear power plant, which is around $75 per megawatt hour. So let's look at from the electrical engineering perspective, what can we contribute to make LCOE to go lower? So what we can really make impact now is just the electrical system. So what I could do is I could make a system that is cheaper to reduce the fixed cost, or make the system that is more reliable so we can reduce the operational and maintenance cost, or a system that is more efficient compared to what is already out there would be nice, because you can harvest more energy for the same wind turbine. It means that you can increase the annual energy production. And with all those things in mind, my PhD work here has been focused on an integrated generator-rectifier system, which is functionally and hopefully physically integrate both power converter and synchronous generator together. So let's look at how the system looks like. This type of system relies on a permanent magnet synchronous generator, which is split into two portions. One portion provides a back EMF of EA will power an active rectifier, and a bigger portion which provides a back EMF of EP will power multiple passive rectifiers. Then we have the DC output of those rectifiers serially connected and send power to a grid interface. So a key feature of this system is majority of the power is going to be processed on the passive rectifiers, and consequently the active rectifier only processes partial of the total power. Because of that reason, the size of the active rectifier is going to be reduced. The second benefit is because the passive rectifier doesn't bear the switching losses, so majority of the switching losses is going to be eliminated, and thereby improve the overall conversion efficiency. And last but not least, because we rely on diode, which is very reliable component, and it doesn't need any control circuit, it doesn't need any measurement devices, so the overall reliability of the system is expected to be improved. With all that in mind, it could help reduce the LCOE to make offshore wind a more competitive energy resource. So the work I have done so far has been focused on power electronics, but because this is a highly integrated system, so a co-design of both generator and power converter is necessary in order to fully take advantage of this architecture. So in this work, we propose a co-design framework for both power electronics and generator. The design framework includes two stages. The first is the design stage, and the second is the assessment stage. For the design stage, three sub-steps are going to be carried out. The first one is the initial generator design, which is making setting the dimension of the generator such that the power and the speed requirements are met. So output of this generator design is going to be a per unit inductance XLPU. The reason why it needs this parameter will come clearer in the subsequent explanation. So the XLPU is first passed to the power electronics design, which is deciding how do we split between the active rectifier section and the passive rectifier section to the number defined as split ratio. After that, the information about the active rectifier topology, the minimum generator speed, and the switch voltage rating is incorporated in order to decide what should be the back EMF the generator will provide. And when we have those the back EMF information, the last step in the design stage is a final generator design, which will decide the generator number of turns in order to meet the voltage requirements. So because of the nature of the design process, is rely on the generic algorithm for generator design. So multiple design points are going to be generated. Because we have multiple design points, an additional assessment stage, which is applied to all the feasible points to select the best candidate, is necessary. So why per unit inductance XLPU is crucial for this design stage. That is because the generator per unit inductance XLPU is independent of the number of turns in each coil, or also independent of the terminal voltage. So in particular, if you consider a generator here, and in each coil in the generator, there's N turns. So the coil inductance is proportional to N squared. And if we calculate the base impedance, which is Z base, it is again proportional to N squared. And when we consider the per unit reactance, it is the reactance of the coil divided by the Z base, which turns out to be independent on N. But why we are considering this quantity? Because from the power electronics perspective, the per unit generated inductance is an essential essential parameters. So in particular, if you want to design a power electronics, you want to select a split ratio K such that the active rectifier volt ampere rating is minimized. The minimization will ensure that you can deliver the power, but at the same time, you only need to use a smallest size active rectifier. And you see here when we change the XLPU, for example, from 0 to 0.1, then the active rectifier is going to change as well. And it turns out XLPU is the only parameter now that is set the active rectifier volt ampere rating. So because of that reason, you see that for each generator, there's a single value for XLPU, and for that XLPU, the power converter is tailored for that particular XLPU quantity. So far, we have seen that the design carried out only in per unit system, but in order to finalize the design, we need to set the voltage level. So with the XLPU, with the process we talked so far, there's two ways to set the voltage level. The first way is going to be the generator set predetermine the voltage level, and the power electronic will need to match that voltage level. The second way is we can the power converter will decide what voltage level the generator should be, and the generator will set the number of turns to match the voltage level. So for our work, we decided to go the second route because at high power level, the options for the switch voltage is very limited. So we want the power electronics to decide the voltage level such that we best utilize the power electronic switch. And if we take that route, the voltage level could be decided by looking at the active rectifier voltage rating. And according to the work so far, we see that at the minimum generator speed, the active rectifier has the highest voltage rating in per unit. So for example, if we consider the system here, at the minimum speed of 55% the rated value, the per unit voltage of the active rectifier is going to be 0.75. And at this stage, we need to know how much voltage does 0.75 correspond to the actual value. So for example, if you choose the active rectifier to be a 3-level converter and you use a 4.5 kV switch, then we can say, oh, if we let the voltage safety margin to be 4.5 kV, then this converter can provide at most 4.5 kV DC side voltage. And that 4.5 kV corresponding to 0.75 per unit. And we already know the V base is 1 per unit. Then just by doing linear scaling, we can back out what is the base voltage for the system. And then you can know what should be the generator back EMF. And because we already have the generator dimension, therefore we can back out what should be the number of turns for the generator. And this will finish the whole design process. So let's look at some results. So if we go, we illustrate the concept using the slotless generator design because in order for the passive rectifier to effectively being used, then a low synchronous inductance is required. And we know the slotless topology will give a low synchronous inductance. This is the generator design result. We see that there's a lot of points. They all have a fairly high conversion efficiency. A lot of them will go over 95%. And just for your information, the state of the art for generator design for offshore application now is standing at around like 94.5 conversion efficiency. And there's an interesting trend here is when you reduce the per unit inductance, you will see the conversion efficiency actually get improved. That is because when we have a low synchronous inductance, more magnet is added to the system to effectively have a larger air gap in the generator, and a larger air gap will lead to a lower inductance. So because we have more magnets, then we reduce less current to achieve the same amount of power. Because less current will reduce the I2R losses. So those designed with a lot of magnet tends to have higher conversion efficiency, and at the same time has lower per unit reactance as well. From the power electronic perspective, we are trying it with a 3-level converter and with 3 types of switches available at high power: 3.3 kV, 4.5 kV, and 6.5 kV. Why 3-level converter? Because this is we found that this is the trend in the high power drive. A lot of companies are trying to push toward the 3-level converter because it can provide relatively high voltage capability, and it could have pretty good conversion efficiency as well. So you see there are 2 trends here. The first is the conversion efficiency is dependent on the switch selection. So for the switch we consider 4.5 kV IGBT provide the best conversion efficiency. And the second trend is within each group of IGBT, you see a lower weight will give you better conversion efficiency. That is kind of counterintuitive because conventionally in power electronics or in machine, a more heavy system is usually more efficient. So this is why, because the lower weight for integrated generator rectifier system, the lower weight will correspond to a narrower speed range. For a narrower speed range, it allows us to boost the DC side voltage to be a higher value. And at a high DC side voltage, in order to deliver the same amount of power, you need less current. And because you need less current, it means that your ohmic losses is reduced. That is the reason why you see lower weight here correspond to a higher conversion efficiency. So when we put everything together, we see the overall electromechanical conversion efficiency, and we compare it with a conventional system. So you see that the net conversion efficiency of the conversion system is standing around 91.5% versus the integrated generator rectifier system. If we do it at the same way, you can get to close to 97%, which is a very impressive number. And even when you stand at the midpoint, you will enjoy the increase in conversion efficiency of around like 4 to 4.5%. So the next question is, we have a cloud of design. Which one should we pick? Should we pick the best conversion efficiency one, or should we pick the lightest one? I would say like neither of the option is a valid one, and we need to incorporate a real wind speed distribution to evaluate the LCOE of the system to pick the final point. So the first step of the LCOE is look at the annual energy production. So you see that if we stand for the same wind speed distribution that we consider, if we use a conventional system, we will get around like 26,700 megawatt hour per year. And if we use integrated generator rectifier system, we can boost up the annual energy production by, you can see, up to like 5 or 6% per year. And on top of that, because we have been relying a lot on diode, and we reduce the voltage requirements on the active rectifier, so we see a lot of decrease in the failure rate of the whole system across the. We look at the time frame of 15 years, which is way exceed the lifetime of a wind turbine system, and we see the failure rate could be reduced by almost 10 times. With the failure rate, it means reduced. It means that you can operate the system for more hours per year, and that would translate to you can extract more power from your wind turbine as well. But really, we enjoy a lot of benefits, but it really doesn't come at zero cost. Because when we look into the total system cost between the rectifier and the generator, we see there's increase compared to the conventional system. This increase because we rely on the generator that has low inductance, and with low inductance generator, we need a lot of magnet because the magnet is fairly expensive. So even though the rectifier cost is reduced, but the increase in the generator cost will make the total electrical system cost increase. But really, is it the cost increase? Is it something we have to worry, or to what extent should we worry about? So we think that the final number to evaluate if a solution is good or not good should be the LCOE. It shouldn't be only on the fixed cost number. And we come back to the original equation. We calculate the LCOE for all the proposed design, and we see that for the conventional system, the LCOE using integrated generator rectifier system, we can reduce the LCOE by around 6.5%. And very interestingly, we see that the lowest LCOE design is neither minimum weight nor maximum rated conversion efficiency. And this point, further corroborate the assessment being done on all the feasible design points, so we can pick out the point that provide us the lowest LCOE, and eventually hopefully make offshore wind turbine become more and more popular in the future. With this slide, I want to conclude my presentation and open for Q&A. If you have any questions, please let me know. Thank you. Yeah, so I guess.
So I guess I'll ask a question here.
Yes.
You may have touched on this, and I'm sorry, I was looking at other things during parts of this. How much of this is very specific to the offshore wind as opposed to something you could apply to onshore wind as well? Like, it seems like any of these cost savings and any of this better design is going to apply to an onshore wind turbine as well.
Yes, Andrew. It could be applied, but for the onshore wind, the doubly fed induction machine is a dominating technology. And they can make it really, really cheap. The reason we are looking for this, but there's a weak point of the doubly fed induction machine, is it will require a gearbox, what is very prone to failure in the offshore condition. So that is the reason why they are shifting to the permanent magnet technology for offshore, and that is with the permanent magnet, it will eliminate the gearbox. But unfortunately, the cost will be significantly higher compared to the doubly fed induction machine. So in the onshore condition, it is more favorable, where the corrosion is not that bad. It is still more favorable to use doubly fed induction machine, and that is the reason why you see that the onshore LCOE is very low. It's already 40 dollar per kilowatt per megawatt hour. And if now we use the same technology for onshore, we would expect the number, it would not be less than $40 per megawatt hour. So there's no point using this technology for onshore wind.
Okay.
Yeah.
I have a question, Phuc.
Yes.
So on this slide, it seems offshore wind turbine cost of electricity is almost like 3 times of onshore wind turbine. And in this case, like, what if we build like 3 onshore wind turbine, like instead of like just 1 offshore wind turbine? Like, what will be the difference? Like, if we just install 3 wind turbines onshore,
Yes.
if we just compare like 3 wind turbines onshore and then 1 offshore wind turbine.
Yes. So if you assume that your onshore wind can run in the offshore environment very reliably, then you should go just take the onshore wind turbine and put it in the offshore condition. But unfortunately, as the reason I just mentioned about that, right now the onshore wind, in order to achieve this low LCOE, they rely on double-fed induction generator, and it requires gearbox. But if you put the same system to the offshore location, maybe in the first month you can still run the system, but on the second month the corrosion starts happening, and you cannot run the system reliably anymore, and the downtime will become like really high, and the maintenance cost in the offshore, whenever you want to do the maintenance, you need to schedule with a ship, with a crew, and in that environment, the cost is very high. So that is the reason why we cannot put the technology that we already have for onshore wind to the offshore locations.
I see. Thank you.
Mm-hmm.
On the failure rate slide, could you go to that one really quick? I have a question about that.
Sure.
For the integrated generator rectifier, why don't we see the same increase of failure rate that we see in the conventional topology?
Yes, you will see, but the rise is like really small. We really need to put it on log scale in order to see the increase.
Okay, perfect. Thank you.
Last call for questions. All right, I think there aren't any more questions. So thank you, Phuc.
Okay.
And that will conclude today's ECE 590 core seminar. So thank you everyone for coming, and thank you again to Megan and Phuc for presenting.
Okay, thank you everyone for joining. Have a good the rest of today.